Good evening, welcome to Pie Shop. Welcome to our socially distanced audience, and welcome also to those of you watching live. Pie Shop takes place every half term, and it's an opportunity for students from any year group to research a little bit of maths that they're interested in and share it with others who want to come and watch. It's quite informal. We normally have tea and cake, and there's opportunities to ask questions. Very supportive audience. We kick tonight off with Barney.
Hi, so I'd like to talk about some indices to start with. So if I start by asking some questions, and hopefully we'll get some responses. So if we look at 0 to the n to start with, does anyone know what 0 to the n is going to give us for any value of n?
0.
Yeah, it's going to be 0, because effectively you're multiplying a bunch of zeros together. So if you do 0 to the 3, you're going to have 0 times 0 times 0, so it's going to be 0. So 0 to the n is always 0. Now, if we look at m to the 0, what's that going to give us?
1.
It always gives us 1. Does anyone know why that is? Any clue? It's effectively, if we look at 2 as an example, so we've got 2 squared. 2 squared is 4. 2 to the 1, that's going to give us 2. So logically, what we're doing each time, we're halving. So if you went up 2 cubed, it's going to be 8. So you're halving to get 4. And you're halving to get 2 again. So 2 to the 0 is going to give us 1. So now let's consider that consider the case where m equals n equals 0. Therefore, we can say that 0 equals 0 to the n, which we know equals 0 to the 0, which we know also equals m to the 0, because we know m equals n, and therefore it equals 1. Does everyone get that? So therefore, we've essentially proved that 0 equals 1. Does anyone know what's gone wrong here? Okay, let's take a step back, and we'll consider y equals x to the x. The issue we've had originally up here is that we haven't considered the case where m equals 0, where we're doing, or n equals 0. So we can't do 0 to the power of 0, because we assume, from what we've written up here, that m to the 0 equals 1, and n to the 0 equals 0. But we haven't considered what happens when n or m equals 0. So I think a nice way to look at this is by looking at y equals x to the x, and seeing what happens as we reach the point where x equals 0. Let's plot a graph of this, I think is the nicest way to do it. So if you think about it, can we have some points on the line y equals x to the x? So I pick an x coordinate, and from that you can work out the y coordinate, tell it to me and we'll plot it.
1, 1.
So 1, 1, yeah, that's an excellent point. What other points have we got on that?
2, 4.
2, 4, yeah. Anything in between? Anyone work that out in their head? No clue. Okay, let's look at it a different way. Let's look at the turning point. And let's assume that there's a turning point, because at the moment this would look like it would go down through here somewhere, and it's going to reach 0 at a negative number, potentially negative 1. But let's have a look and see if we can find a turning point anywhere. So, to find a turning point, we differentiate. So we need to try and differentiate y equals x to the x. Does anyone have a clue how we could go about this and how we could start differentiating that? Okay, the methods that we'd use to do this might be a little bit complex for some of our audience. So if you have any questions, let me know. And if you're a bit close about what's going on, bear with me, because you don't really have to understand what we're doing to differentiate to understand what we've differentiated to. So what we're going to start by doing is taking ln of both sides. So ln y equals ln x to the x. Ln is log base e, and if you don't, e is a mathematical constant, so it's similar to pi. It's just a number, and log base is taking a logarithmic of something. So if, for example, you consider 3 to the x equals 2, and you want to work out what x is, you use a logarithm to find that. So it's a way of finding powers if you've got the base and the answer. So we're taking ln of that, which is log base e of x, which is what this is going to be. So log base e of x is ln of x. And we need to differentiate, therefore, ln of y and then ln of x to the x. We can use rules of logarithms to find out that actually this is going to simplify. Ln of x to the x is going to simplify to x ln x. That's just a basic rule of logarithms that we can apply. And then we need to differentiate this, which we could use a multitude of methods, probably some of which that most of you won't have covered, but that's not necessary. You don't have to necessarily understand that to understand what's going on. So to differentiate the right-hand side here, we use something called the product rule. And the product rule is used, if I write it over here, product rule is used when we have something, for example, y equals f of x, g of x, when you're multiplying two functions together and you need to differentiate that. So in this case, the product rule is y dash, which is what happens when you differentiate something. You get that dashed. Is going to be f of x times g dash of x plus f dash of x times g dash of x times g of x. So, if you're considering that, does anyone know how they differentiate x ln x? Does anyone want to try and do that? Let's look at the right. Let's look at the left-hand side to start with. So you're looking at x. So if we consider x as f of x, it's going to be x times. So if we look at the left-hand side, the bit just here, it's going to be x times g dash of x. So we need to differentiate ln of x, and ln of x differentiates to 1 over x. So it's going to be x times 1 over x. So it's going to be 1. So we know this is going to be 1 times something. So now if we look at ln of x, which is going to be our g of x, this bit over here, we need to do f dash of x. What does x differentiate to with respect to x? It always differentiates to 1, correct? So it's going to be 1 times g of x, so it's going to be 1 times ln of x. Sorry, it's going to be 1, plus. Apologies, so it's going to be 1 plus ln x. Now we need to differentiate the left-hand side, which we're going to use something called the chain rule for. Now the chain rule is used, I'll write this on the side again, the chain rule is used for functions inside functions. So for example, if you had f of g of x, that would be something you would apply the chain rule to differentiate. And the way the chain rule works is if you let u be g of x, if you let u be g of x, then your dy dx, what you differentiated to get, is going to be dy by du times du by dx. So if we now apply that to our left-hand side, ln of y, this is going to become 1 over u, and we know our u here is going to be y, so it's effectively 1 over y. So 1 of u times, and then we're differentiating y with respect to x, we just get dy dx equals 1 plus ln of x. So it's going to be 1 over y by dy dx equals 1 plus ln of x. And therefore, if we multiply both sides by y, we're going to get dy dx equals 1 plus, y of 1 plus ln of x. And we know from back up here that we've let y be x to the x. So this is going to be x to the x times 1 plus ln of x. So that's our gradient. That's our gradient function. And from that we need to work out the turning point, which is hopefully going to be somewhere on our graph, and then we can work out from that where we go to find out what happens when x equals 0. So, any ideas how we're going to be able to find a turning point from this? You have to understand what we've done to get here. Just does anyone know how you find a turning point? from a gradient function? Yeah, equals, is that what you're going to say, Ralph?
Yeah,
So we're going to make it equal 0. So we know x to the x of 1 plus ln of x equals 0. So this doesn't help us a huge amount because we either know now that x to the x equals 0, because because this is the way it tends to work with these kind of things, that you only need to make sure that the one on the left is 0, and you need to make sure what's in the bracket is 0. So we either know that x to the x equals 0, or 1 plus ln of x equals 0. So this hasn't helped us a huge amount, but if we look at this 1 plus ln of x, and now I'm going to go into GeoGebra, we actually find that the turning point is around here somewhere. I don't want to go into a huge amount of working it out, but there is a turning point, and it's here. And if you look at it, it looks like we're going to cross the x-axis at 1. So that's going to tell us that 0 to the 0 is 1. However, if you zoom in really close, and you keep on zooming in, which we're probably not going to be able to do here, you're actually going to see that it doesn't ever meet the y-axis, that this line never touches the y-axis. So that kind of raises more questions for us, that actually, if we graph it, there is no true value for 0 to the power of 0. So if we look back to what we started with, we're doing 2 to the 2 equals 4, back up here. 2 to the 2 equals 4, 2 to the 1 equals 2, and 2 to the 0 equals 1. And then we apply that to what we're trying to do with 0 to the 0. So if we do 2 to the 0, we know it's going to be 2 to the 1 over 2. We know that n to the 0 equals n to the 1 over n. And therefore, we know that 0 to the 0 equals 0 to the 1, which equals 0. Does it? Yeah, equals 0. Over 0. And our issue there is that we're trying to divide something by 0. And this, yet again, leads us back to... Well, does anyone know what happens when you divide by 0? Is anyone aware of that? Yeah, not a huge amount. It becomes undefined. Well, you can't divide by 0 is effectively what we're taught. So that kind of brings us to the conclusion that you can't actually do 0 to the 0. There is no true value for it on a graph. And you can't divide by 0 when going through this method. So that leads us to the conclusion that 0 to the 0 is in fact undefined. Anyone got any questions? Thank you very much.
And hopefully Barney's quick tour of calculus has inspired some of the younger years to want to find out more about that area. Thank you very much. I'm handing over now to Alexander, who is going to show you how to solve a cubic.
Okay, cool. Right, so for my presentation, I decided to look into cubic equations. So I think everyone should know that we have a quadratic equation. So we know that this is the minus b plus or minus the square root of b squared minus 4ac, and then that all divided by 2a. And that's something we're taught in year 9, okay? So what I want to look at is if there's actually an equation for solving cubic equations. So that is equations of the form ax cubed plus bx squared plus cx plus d, and that's equal to 0. And after a bit of research, I did find that there was an equation for solving cubic equations. So hopefully in this presentation I'm going to derive it for you, show where it comes from, maybe a bit of history about who first came up with it. So first, we're going to assume that this cubic equation is very simple one, so where a is equal to 1. You can get other equations where a isn't 1, but all you'd have to do is divide all the terms by a, and that would equal, you'd get a is equal to 1 then. So to derive this equation, what we need to do is something called depressing the cubic, and it's a method thought up by Cardano, who was an Italian mathematician and physician. And what he used was this method of depressing, which is a way of using a substitution. So we say x, if we let x equal to y minus b divided by 3, then what we can do is we can substitute this in to that equation there. So we'd see that x cubed, well, that would be y cubed, sorry, y cubed minus by squared plus b squared y over 3, and then that last one term is going to be minus b cubed over 27. So that's if we expand that out. We also see that x squared, we're going to get y squared minus 2b y over 3, and then plus b squared over 9. And then we've already said that x is equal to y minus b over 3. So then we can rewrite this whole equation as, if we combine all of the terms, we get y cubed minus by squared plus b squared y. I think I may have run out of room here, so I might just I'll keep going, but minus b squared y over 3 minus b cubed over 27 plus, and then what we're going to do is we're going to take this x squared term, we're going to times it all by b. So we're going to get b y squared, then we're going to get minus 2b squared y over 3, and then we're going to get plus b cubed over 9. And then, just like again, we're going to times this x term, we're going to times it all by c. So we get plus c lots of y, so cy minus cb over 3. And then we're just going to add d at the end, because that doesn't have any x terms in it. And all of this is going to be equal to 0. So we can do a bit of simplifying now. So we can see that if we times all the numbers by, basically get rid of the denominator, so to make it a bit simpler, and if we get the y terms collected, we've got this, I'll change colour just to make it a bit clearer. So we've got this minus by squared, and we've got by squared, so we see those cancel. And then if we look at the y terms, we've got b squared y over 3 here, and we've got minus 2b squared y over 3. So that just becomes minus b squared y over 3. And then you've got the c term, which is another of the y terms, that just stays the same. And then you've just got all the terms which don't involve a y, so you've got minus b cubed over 27, b cubed over 9, and minus cb over 3. And with a bit of simplifying, just change it to that, we get this equation, y cubed plus c minus b squared over 3, times that by y, and then we get this plus 2b cubed over 27 minus bc over 3 plus d. Sorry, my handwriting's not the best, but you see that that is equal to 0. And now what we've done is depressed that initial cubic equation, and we've got it into this form, which is x cubed plus px plus q. You can see we've got rid of the y squared term altogether, and that's really what we're trying to do here. What we're trying to do is we're forming this sort of simplified cubic equation. Because now what we can do is we can look at two scenarios. We can look at when p is equal to 0 and when p is not equal to 0. So when p is equal to 0, it's very simple to solve this equation. The x term just cancels out, so we get x cubed plus q is equal to 0. And then we can solve it So we get x cubed is equal to minus q. So then we get x is equal to the cube root of minus q, where x belongs to the complex numbers, because we're square rooting a minus number. So that's relatively simple, but of course we know that we're not always going to get a nice simple equation. We might get an equation where p isn't 0. So what we'd then do is we depreciate it again, basically. So what we do is this time we let x equal u minus p over 3u. And then we do this whole depressing thing again. Sounds a bit bad, but I don't know why they came up with that name. But so what we do then is we sub that in. So we get y minus p over 3u. That's all going to be cubed, because that's the initial, this term here, we're going to cube it. Then we're going to add p lots of u minus p over 3u. And then we're just going to add q. And again, that's equal to 0. And then we can do a lot of expanding here. So we could use the binomial expansion here, and we can see that this first term here, well, that's going to be equal to y cubed minus 27, oh actually, sorry, minus 3u squared times p over 3u, and then added onto that we get 3u p squared over 9u squared, and then we get minus p cubed over 27u squared, sorry, u cubed, and that's going to be that first term expanded. And then for the next term, you're just going to get plus pu and then minus p squared over 3u plus q, and that's going to be equal to 0. And then again, we can simplify it more. We can find common denominators, and then this equation will simplify to u cubed minus p cubed over 27 u cubed plus q, and that's equal to 0. So for that, what we've done is we've made a common denominator of 27u cubed for this term, this term, this term, and this term, and it's simplified nicely just to give this one term. And now what we're going to do is we're going to times all the terms in this equation by 27u cubed. So we get 27u cubed to the power 2 minus, sorry, plus 27u cubed times by q, and then minus p cubed. Can anyone spot perhaps where we might go with this? Yeah, that's right. So it's a quadratic in disguise. So now what we can do is we can go back to that quadratic equation which we're all familiar with, the minus b plus or minus the square root of b squared minus 4ac over 2a, and we can use this to solve for u cubed. So if we let u cubed equal to x, or in fact we don't even need to do that, we can just substitute it in straight away. We can say u cubed is equal to minus b, which in this case is 27q, plus or minus the square root of b squared, which is going to be 27 squared q squared, minus 4 lots of a, which is going to be, may not be able to fit this in, 27, and then put brackets here, 4 lots of a times by c, so c is minus p cubed, so times by minus p cubed, and that's all going to be over 2 times a, so it's going to be 2 times 27. So now what we can do is we can simplify it a lot actually. If we rewrite it and put the denominator as the square root of 4 times 27, so that's going to be minus 27q plus or minus the square root of 27 squared q squared minus 4 lots of 27 minus p cubed. And then we're going to write this as, first off, we can cancel the 27, so we get minus q over 2, because the two 27s cancel here. But for the main square root, what we can do is we can rewrite the denominator as the square root of 27 squared, and we can just say 2 squared and say that's 4. So we can rewrite it as plus or minus the square root of 27 squared q squared minus 4 lots of 27 minus p cubed over the square root of 4 times 27 squared. And then we can simplify this because we've got root 27 in common in all of these. So we can say it's equal to minus q over 2 plus or minus the square root of minus q over 2, because the q's we can say that's sorry I misread that. So it's going to be q squared over 4, because the 27's cancel here, but it's going to be divided by 4 here, and then it's going to be minus the 4's cancel here, and then you've got the 27, one of the 27's cancel, so you'll get minus p cubed over 27, and that is all equal to u cubed. So now we've got this expression for u cubed. So what we can do is we can find u, and u is equal to the cube root of the square root. So it's going to be the cube root of minus q over 2 plus or minus the square root of q squared over 4 minus p cubed over 27. And so normally for a cube root, when you cube it, you will get 3 answers. But in this case, because we've got this plus or minus square root inside here, we'll actually get 6 answers. And so now we've got this expression for u. And now at the start, we said that x is equal to u minus p over 3u. So therefore, we can sub in the value of u here into this equation, and we can get this cubic formula, which is for x is equal to the cube root of minus q over 2 plus or minus the square root of p squared over 4 minus p cubed over 27 minus p over 3 lots of this whole equation here, which perhaps I'll spare you writing out again. But yeah, so I'll just write it out just for the maybe another line will be in need.
I'm sure we can imagine it.
Yeah. So over 3 lots of that.
You could just call
And
it 3u.
3, yeah, where u is this equation here. So yeah, that's actually the formula you can use to solve a cubic equation. I think perhaps maybe using your calculator is a bit simpler, but I think this is also quite interesting. It's good to know we can actually do it. We don't have to rely on a calculator to do everything. So yeah, so just to recap, what you do is you get your cubic equation, you depress it, you get it in the form x cubed plus qx plus px minus q, and then you can just plug it into the formula. And I don't know how many marks I'll get you on a GCSE or A-level maths paper, but I'd hope it'd be a lot. And yeah, that's it. That's a cubic equation.
Thank you very much. Absolutely perfect timing. We'll take questions in a second, but we'll just wrap things up for our live audience. So thank you very much,
Thank you.
Alexander.